Hey guys, my name is Daniel Koffler. I'm CTO of Rio Tinto Alcan. I'm going to talk to you today about closing the data loop, so managing the convergence of software, data, and industrial physical assets. So Rio Tinto is a large mining conglomerate. Mining and manufacturing. We've got 6 product groups. Just to give you an idea of our scale, we're the number 2 producer of aluminum, number 5 in copper, number 2 in uranium oxide, and number 3 in diamond production worldwide. So we're a large company, very diverse portfolio. Basically, the saying at Rio Tinto is, if it's a mineral and in the ground, we dig for it. Now, I work for the aluminum group, and one of the interesting things about aluminum is it's not just about, you don't dig aluminum out of the ground, you dig out an ore called bauxite and manufacture it into aluminum. And I'll talk about the process in a couple of minutes. So we're really a global company. We operate pretty much everywhere there are major populations. You can see on the map we've got quite a large footprint in Australia and North America. South America, we're just sort of starting to ramp up, and we own a number of companies and have lots of sites all over Europe. So just to give you an idea, I'm relatively new to Rio Tinto, and one of the things I'm still struggling with is wrapping my head around the scope of our operations. So here are a couple of shots of some of our sites. You can see they're rather large industrial environments. I'm going to show you one of the bauxite mines I was telling you about. So the marker on the map is for our Weipa mine in northeastern Australia. Just to give you an idea of the size of it, you can see down at the bottom left of the image, you can see a bit of brown. That's our mine. When we zoom in a little bit, this is our area of mining operations in one particular site in Australia. And I'll show you a comparative slide later on, just how massive this one particular site is, and this is one of many. So a typical aluminum plant setup, and this is the manufacturing process. You pull the bauxite out of the ground, you put it through an initial chemical process which extracts what's called alumina from the bauxite, and then the alumina is put in these huge carbon vats with what's called the bath, basically a mixture of different chemicals, and then we zap it with an enormous amount of electricity. Our latest technology, and you can see the row where it says electrolysis there on the slide. That huge long row, that's about 1.5 kilometers long. That's just pots filled with alumina and the bath. And we send about 600,000 amps of electricity through each of the pots in a serial setup. So just to give you an idea of the type of harsh environments we're talking about, you can imagine the harsh environment in a mine, even a surface mine. But in the electrolysis plant, we generate so much electromagnetic radiation that vehicles in the plant often become magnetized, and tools will stick to them. Any type of IT equipment that has any sort of magnet in it, so when we used to have hard drives, right, these things would get fried left and right. The operators, in the old days when we had CRTs, the operators couldn't really see the screens when the plant was running because the EMP fields would just mess with the CRT cathode gun. And then we have lots of other stuff. So the aluminum product group alone, we own 4 railways. We have lots of shipyards and ships. And then top right there, that's one of our hydroelectric power plants. So we own and operate a number of hydroelectric dams all over the world to generate the electricity needed in our production process. So why the Internet of Things? Why am I at Solid? And what are we talking about? Well, really, our industry has started a radical change. And it's so radical, we're not even sure how we're going to deal with it in the long term. And I'll share with you some of the initiatives we've already put into place and how this has already transformed our industry significantly, and how it's going to, you can extrapolate from that, how it's going to transform many of the other manufacturing and heavy industries. So basically, we come from a long line of mining companies, and this is what most people think of even today when you talk about mining. Guys down in the dirt, manually breaking apart rocks and digging ore minerals out of the ground. And up until very recently, this is exactly what operations looked like, except for maybe the child labor in the middle slide. But up until about a decade ago even, this was the type of operation we had. Guys with shovels in the ground. You'll notice bottom right, there's a guy standing about 3 feet away from a huge vat of molten aluminum. That aluminum's at about 2,500 degrees Celsius, and he's casting it. He's pouring it. This is part of the casting house operation. He's pouring it into cast to make ingots out of it. So you can just imagine the safety issues being that close to molten aluminum. There's all types of fumes that come off of it, in addition to, obviously, the heat and burn hazards. And so where we are today and recently is, we're going through a shift and a real automation adoption shift, which is really changing our operations. I love this slide because it really shows the dichotomy going on within our industry. In the top left, you can see the miner, and he looks like a typical miner, like a guy who would be down in the dirt. He's even wearing the hard hat, but he's sitting in an office. And he's remote controlling that machine in the bottom right that has no operator in it, right? So he's got full remote control of that device, and yet it shows, again, sort of the cultural shift that's going on. Even though the guy's not on site in the ground, he still is ready and looks like he just walked out of a dig site. So, in addition, we're moving to what we in Rio Tinto call the mine of the future, which is trademarked if you want to use it. You can talk to our legal department. So really, it's trying to gain, how do you gain a competitive advantage when you're dealing in a commodity business, you're selling to really an open market. Basically, everything we make goes to the London Metal Exchange. There's not a lot to differentiate on the product side, although there is some, but really it's a commodity business. So how do we use technology to gain a competitive advantage in this type of environment? So it's all about efficiency and really driving costs down and production efficiency to its maximum. So the top picture here are autonomous haul trucks. So these trucks are fully autonomous. There's not an operator in them. They will navigate the mine site. They will go to the diggers, wait to get loaded up, and then take a route home, all without any human intervention required. And then at the bottom, you see one of our rail systems. Next year, this is going to go live. It's in testing now. This is going to be the first heavy haul network in the world to be fully automated. So no human intervention required from end to end. This is a first worldwide. And so it allows us to move more ore, more consistently, without human intervention, without fatigue, operator fatigue, and less maintenance required. So again, it comes down to really two reasons why we're looking at technologies in this space. The first is, as I mentioned, increased production at lower cost. The bottom line is really one of the driving factors in pretty much everything we do. GE talks about the power of 1% in its industrial internet stuff. And here's just a quick slice of some different industries and how a 1% efficiency increase can really translate into millions or billions of dollars. So you'll notice that a lot of these are around 1% fuel savings or system efficiencies, right? And then in the oil and gas industry, it's interesting. The 1% reduction in capital expenditures is estimated to translate into a $90 billion savings over 15 years. So this isn't exactly chump change for just your 1% increase in efficiencies. And we see the same type of things at Rio Tinto Alcan in our aluminum business. Currently, we're spending $3.1 billion on power for the smelters, $306 million to replace the pots in which the electrolysis happens, and $37 million annually in energy for our furnaces to bake our carbon cathodes. So a one increase in efficiency in these systems, we're estimating is going to translate into a 33.5 per annum savings for our business. The second major reason is safety. So health and safety is one of the driving factors throughout the Rio Tinto conglomerate. We're really focused on zero harm by choice, and I'm going to show you some examples. So micro sleeps. This is, if any of you have ever been at a boring conference, or obviously not this one, or in a class, and you've had that moment where you nod off and jerk awake, or that sudden feel of falling, that's a micro sleep. And you may just be out for a fraction of a second, but the consequences can be really grave when you're operating heavy machinery. So here we see two actual micro sleep incidents. And these are things that happen really in a fraction of a second. So what did we do? We implemented with a partner company in Australia a bioinformatic feedback mechanism called the Smart Cap. And this monitors the brain waves of the operator in real time and indicates the fatigue level of the operator and their state of mind. And as you can see from the network diagram, we can collect this data from the operators on all our systems simultaneously and basically manage it from a central operations center. The second part is conveyor maintenance. So we run conveyors that carry minerals. Some of these conveyors can be over 30 kilometers long. And so here you see them going, and you see those spinning wheels. Those are what moves the conveyor belt. And replacing these can be very costly, and I'll show you why. Because this is how normally you would replace one of those spinning wheels. The guy has to come through with the jack, and you'll notice the conveyor here is stopped due to worker safety reasons, right? You don't want this speeding conveyor going on while this guy is working. He jacks it up and manually pulls out the offending pin and then replaces it. We won't go through the whole video, but you can see it's a very manual, intensive process. It's slow. We just this year deployed a new robotic method of doing this. And one of the things you'll notice as this video goes, see it's jacking up the conveyor at the moment, but the conveyor is still running. So that means we didn't have to stop production. We're not losing any money for the maintenance. This is going to reduce our total downtime significantly on these type of systems. And the next stage, what we're rolling out in the next couple of years, are sensor networks along the conveyors and automated autonomous vehicles that will go and measure the health of all the parts, all those things that spin on the conveyor, and we'll be able to dispatch this robot, again, in an autonomous fashion, so it will go and automatically maintain our equipment. Here's one other thing. We did an interesting experiment a couple of months ago where we ran a hackathon in Australia. And basically what happens in our iron ore operation is we have crushers that crush the rocks that come out of the ground. But if these rocks are too big, they can jam the crusher, and that can require several hours and up to 2 days of maintenance where that whole production line goes down. At this hackathon, some university researchers came up with this idea of using acoustic sensors in the conveyors leading up to the crusher. And so now we can visualize the exact size of each piece of rock that's on that conveyor, and we can preventatively remove the ones that are too big or might pose a threat to our equipment. Again, we're preventing downtime and doing what's called predictive maintenance. So this is another GE slide on the internet data loop. And basically it goes from instrumented machine to data acquisition, analytics, visualization and control, and then over the network, sending new information back to the machines. So this part is easy, and this is really just remote control, and pretty much everyone here is familiar with these type of systems. And this part also isn't that difficult. We're now instrumenting machines, the whole big data movement. We know how to collect this data and how to do parts of the analysis. But tying this whole thing together is really still a challenge, and I'm going to show you what we've been working on. So the network part generally is considered easy, right? Except for when you're in Northern Australia or other remote parts of the world where getting actual WAN connectivity or data connectivity is very difficult. So you can see running a fiber link from Perth to our WIPA mine that I showed you before, that's like transiting 3/4 of Europe. Just within that region. And this is something we have to do and that we do often. But when those links go down, time to repair can be quite difficult. So what do? We deploy lots of wireless antennas all over the place. But we're operating in Northern Australia. So every once in a while, Mother Nature will send a cyclone our way and knock all those fantastic antennas down to the ground. And in a fully autonomous system, what are you to do? So we're using things like lighter-than-air dirigibles that can take communications package up and float out until we can get the towers repaired. We're looking now at long-term drones to carry similar communications equipment. So basically, every piece that we're working with, we have bolts that have Bluetooth on them. And so we're collecting all this data, and it allows us to use totally automated drilling machines, autonomous haulers, and in the bottom left you've got an autonomous survey vehicle, which we use to survey our sites. We can use it for site security as well. And I'll show you what that allows us to do. I'm running out of time, so I'm going to skip through. But basically, the amount of data we're collecting is just growing exponentially, and we expect it to keep growing. So here's a 3D model. This is the visualization we've started to do. We're using the Unreal Engine for this, actually. So all my wasted hours as a youth gaming are finally bearing fruit. So, take that, Mom. Here's the actual physical automated drilling machines, autonomous drills, and then their virtual representations. And it lets us see into the ground where the ore deposits actually are. We're now getting millimeter by millimeter data readings of how hard the material we're digging is, and where our we have a much better idea now where our ore deposits are. This is another great visualization. These are our autonomous vehicles. The ones in green have a topped-up fuel supply. The two that are in yellow, they're at the medium point of their fuel. So in real time, we can see the fuel level, we can see how much tonnage each of these machines is carrying, and we can see where they are. And so we have all these different visualizations, and really what we're doing is we're getting to the point where we've got these processing excellence centers, which basically we're centralizing all our subject matter experts, and they're able to collaborate and find variances across the globe. So we may have mining operations in Peru and Australia that have a similar problem. We can now control them and send information and instructions to the site operators globally from centralizing our subject matter experts. So we call this the Processing Excellence Center. And here's a great slide. You can see the guys marking up the board, and they're communicating in real time with with an on-site technician to solve a problem. And we can do that now from one central location globally. We can reach across the globe through this Internet of Things, all these connected devices, and solve our problems, increase our efficiency, and ameliorate our bottom line year after year. That's it for me. Thank you very much. If anybody has any questions, please feel free to grab me after the show. Thanks a lot, guys.